Now we'll look at a more complicated example. We'll examine single particle Fermion Hamiltonians with multiple fermions. What we mean by a single particle Hamiltonian is that the Hamiltonian of any one fermion can be written entirely in terms of that fermion's properties and coordinates. For example, we presume one fermion's energy does not depend on the other fermions in the system. Equivalently, we're presuming the fermions are non-interacting, or at least their behavior can approximately be written that way. This is a good starting point for multiple uncharged fermions, such as a set of neutrons, so dilute that there are negligible collisions. And it can be used with charged particles as well in some specific situations. A very important example is the single electron model in a crystalline solid. Approximately, each electron moves in the average periodic potential, V of R, created by all the other electrons and nuclei. This single electron approximation decouples the Hamiltonians for the different electrons, giving a total Hamiltonian that is the sum of the single electron Hamiltonians. Here, with our annihilation and creation operator approach, this single particle Hamiltonian form is particularly easy to write down. Suppose then that we have n identical fermions. Fermion I is presumed to have a single particle Hamiltonian in the original R form, such as our simple Schrödinger equation 1. Therefore, in the original R form, the total Hamiltonian for the set of n fermions is just the sum of all of these single particle Hamiltonians. We have to sum the different Hamiltonian with a different coordinate for each of the possibilities of Hamiltonians from 1 up to n. We now show that even for the multiple fermion case, we can still write the total Hamiltonian operator as just this form. Note in here there is no sum over I. So regardless of how many particles are in the system, we do not have to change the Hamiltonian for the non-interacting fermions. That is, we don't have to write down a sum over all the particles. So we don't have to write this kind of sum. So now we're beginning to see some of the power of this different way of writing the Hamiltonian down. So now we consider a single particle fermion operator and a multi-fermion system. We now illustrate that this form is still the Hamiltonian we would deduce when we create the Hamiltonian using multiple fermion wavefunction operators. And we're going to show this Hamiltonian works also explicitly for two fermions, n is equal to 2. Suppose we have a specific two-fermion state with one fermion in single particle state K and one in single particle state M. We can write that state in our occupation number form here, with one particle in state K, one particle in state M, and we can also write that as the creation operator for state M acting on the empty state, and then the creation operator for state K acting on the result of that. Evaluating with our new Hamiltonian form, we have this kind of relation we're going to evaluate. And now that relation looks as follows. So here's our state, psi 2 particle, Tp, so here it is. And here's the Hermitian adjoint of that over here. We've written it with the Hermitian adjoint marked up here. And this set of terms in here, Ej, Bj dagger, Bj, is just with the sum over j here, our Hamiltonian operator. Remember, this sum over j is over the possible states of the system, the eigenstates, not over the particles. This is the usual summation over all the eigenstates. That's the j index. Well, we can simplify that, of course. We can work this out and put all the operators together in the middle. And now we have 6 annihilation and creation operators in one expression. Well, we're going to simplify this expression now. And again, all we're going to do is use this anti-commutation relation to push the annihilation operators to the right. This whole process is one that you almost don't even have to think about. There are no real decisions to be made here. Every time you see a pair of operators with the annihilation operator on the left and the creation operator on the right, you use this relation to rewrite it. So we can start doing that. Note that there are two pairs like that in here. Here's the annihilation operator for state K and the creation operator for state J. So we can substitute for those using the anti-commutation relation. And here's the annihilation operator for state J and the creation operator for state K. So we can substitute for those using the anti-commutation relation. So we can multiply that out and keep going like this. So we've multiplied out this entire expression here. We've got this set of terms as a result of all of that. And we can keep going. So we have annihilation for M, creation for M, so we use the anti-commutation relation there. And since the M's are equal, the Kronecker delta is 1 here. Similarly here, we've got annihilation for M, creation for K, so we rewrite that. We've got annihilation for J, we've got creation for M, so we rewrite that. Similarly in here, we've got two pairs like that, we rewrite those. And in here, we've got 3 pairs like that, so we rewrite each one of them. Note again that this one is BK dagger, so the Kronecker delta is just a 1 here. Well, in this expression that we've just written out, you'll note that we have annihilation operators on the far right everywhere we have these creation or annihilation operator pairs in this entire expression. So all of these terms disappear. Again, because the annihilation operator operating on the empty state gives us 0 for any I, any state I. Hence, this expression just reduces to this string of Kronecker deltas, but by choice at the very start of this we said we were trying to evaluate the energy for one particle in state M and one particle in state K, and of course since these were fermions, these have to be different states. So M and K are different, so all of these Kronecker deltas with M and K in it disappear. Delta MK never has any value other than 0, hence this entire expression simplifies down to this one here. Well, if we substitute that back into our expression for the expectation value of the energy, all we're left with is these two Kronecker deltas in here, which means we only have 2 terms left out of our sum, the one where J is equal to K and the one where J is equal to M. And so the answer we get when we had one particle in state K and one particle in state M is that the energy expectation value of the system is simply the sum of those 2 energies. That's exactly what we expected for 2 non-interacting fermions. So it might have seemed a long and complicated process here, but it doesn't matter. It was actually quite simple to do these manipulations, and what we're illustrating is that that form we wrote down for the Hamiltonian continues to work even when we have multiple particles. And we could have kept on going here, adding in more particles. We would just keep getting the same answer of adding all these single particle energies for these non-interacting fermions. Hence, this illustration shows how the Hamiltonian, written in this form, without any summation over Hamiltonians for different particles, also works for multiple particle states. Unlike the R representation of the Hamiltonian, we do not have to add separate Hamiltonians for each identical fermion. And hence, we have an elegant form of Hamiltonian for multiple fermion systems.